our last sessions, we handled the substitution of a cofunction, right? Now, the last one I'm going to do is type D, which is using the sine squared plus cos squared equals 1 substitution. Okay, these are generally a last resort. Okay, so first of all, let us look at this as type D for your notes is sine squared x plus cos squared x. That was going to be a theta. Cos squared x equals 1. Obviously, sine squared theta plus cos squared theta equals 1. Also, it depends if they've got a sine or a cos in there. Now just remember, okay, this is last resort. Okay, generally. And it is, when do we apply? When a quadratic cannot be factorized. All right, like this, only this, right? When we have got a sine squared x plus b cos x equals c, or a cos squared x plus b sine x plus c equals 0. Can you see that it's the form of a quadratic? This one I would make it a sine squared x plus b cos x minus c plus c, let's say, equals 0. Then it's in this type. What is my problem here? My problem is I've got a sine squared and a cos squared and a sine. Okay, I cannot use cofunctions here. Why? Because I have got a third term c. Remember, it's similar to cofunctions, isn't it? The sine and the cos, but here's a squared, okay, which is making it even more difficult. What you have to bear in mind is this. Remember that sine squared x plus cos squared x equals 1. Therefore, sine squared x is 1 minus cos squared x. Also, cos squared x is 1 minus sine squared x. So we can do a replacement. Okay? So we can replace, we could replace these with those, couldn't we? We could replace them. I'm actually going to, I'm going to take that arrow and make it a different color. Replace them with those, couldn't we? So you can see, let's just have a look what's going to happen. Okay, what is going to happen here is if I replace the sine over here, replace this cos squared with that. So I'm going to get a 1 minus sine squared x plus b sine x plus c. Can you see what I have done, what we have done? We have put sine and sine together. Therefore, we've made it a function that we can factorize now. That's the beauty of this one. Okay. Let's just show you in an example of this. Okay. Here's an example. Minus 6 cos squared x plus sine x plus 4 equals 0. I just want to check. Yeah, that's correct. Okay. Can you just look here? This is like an x and this is like a y, isn't it? They're not the same in the same equation, right? So what do we have to do? We have to do a replacement, okay, of the cos squared with the sine squared. Minus 6, 1 minus sine squared x plus sine x plus 4 equals 0. We always replace the square, okay? It's the square replacement that we do. We don't replace that, because if we replace this one, we would end up with square roots, and that brings us to the K method, and we don't want that. Would you get the same answer? Probably not, because there's so many mistakes that we're going to make along the road. So let's have a look. What do I do now? Okay, we put in that, so that we've got that. Then I expand the brackets, and I get minus 6 plus 6 sine squared x plus sine x plus 4 equals 0. Group like terms, and I get 6 sine squared x plus sine x, and that's minus 2. What do I do next? Next, I just factorize, because now I have made it so I can factorize. Yes, you might have to use minus b plus or minus square root of b squared minus 4ac over 2a for this, sure, but in essence, they're probably not going to give you those kind of questions. It's unnecessarily complicated. This is complicated enough. So we're going to factorize with k equal to sine x and k squared equal to sine squared, or you just factorize and you get 2 sine x minus 1 and 3 sine x plus 2. Plus 2 equals 0. And what do? I then say 2 sine x minus 1 equals 0. 3 sine x plus 2 equals 0. And then I can say sine x equals a half. And sine x equals minus 2/3. And I go reference angle, type, sine, etc. And I end up with a whole pile. We end up in this case with x equals 30 degrees plus 360k. Theta is equal to 150, or x. Keep writing theta. X equals 150 degrees plus 360k. X equals minus 41.81 degrees plus 360 degrees k. X equals 221.81 plus 360 degrees k. And you've always put k as an element of z at the bottom. Okay. So let's have a look at a complete mixture. Let's get the worst possible thing that we can as an example, and let's see if we can do it. Example, minus 4 sine squared theta minus 8 sine theta cos theta plus 6 equals 0. First thing, change the sign. So it's 4 sine squared theta plus 8 sine theta cos theta minus 6 equals 0. Okay. Can you see here that if I replace sine squared, if we replace that with 1 minus cos squared theta, we're still going to have the problem of sine there. So we kind of missed. Okay. Similarly, if we had a cos squared theta plus b sine theta cos theta minus or plus c, can you see if we did a replacement here of a times 1 minus sine squared theta, that's great. There's the sine and the sine, but guess what? I've still got cos. So we are still completely and utterly lost. Okay. Now, I know I've said it before, but this is it. This is the end of the line. After this, computer-aided solutions, here we come. What do? We are going to here make the final possible thing that we can. We are going to change it into this. Okay? And of course, sorry, before. So what did I have? I had 4 sine squared theta 4 sine squared theta plus 8 sine theta cos theta minus 6 equals 0. Highest hang on, I can divide through by 2. So that becomes 2 sine squared theta plus 4 sine theta cos theta, not co-theta, Kevin, cos theta, please, minus 6 equals minus 3. Okay? Minus 3 equals 0. I am now going to replace the following. Okay? Minus and a plus. Okay? 2 sine theta, blah, 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 4 sine theta. Yes, okay, like that. What am I going to do? I'm now going to replace the last part. I'm going to say, this is 2 sine squared theta plus 4 sine theta cos theta minus 3 times sine squared theta plus cos squared theta equals 0. Okay, I have replaced that times 1. I have replaced that with the square identity. This gives us 2 sine squared, okay, and it's going to be this, 2 sine squared theta plus 4 sine theta cos theta minus 3 sine squared theta minus 3 cos squared theta equals 0. Group-like terms are minus sine squared theta plus 4 sine theta cos theta, okay, minus 3 cos squared theta equals 0. All I did is I grouped like terms there, right? I took this guy, sine squared, and added it there and just basically tidied it up a little bit. Okay. Now I'm going to divide through by minus 1 because I don't want a sine minus sine squared. Sine squared minus 4 sine theta cos theta plus 3 cos squared theta equals 0. Now, you're going to be saying to me, okay, well, so what? Do you remember right back grades ago when we had x squared minus 4xy plus 3y squared? Can you see that's like an x squared? It's a sine squared. This is like a y squared. It's a cos squared. And this is the mixture of the two terms. It means that I can factorize this. I can factorize. How do I do it? I say to myself, right, this is sine theta minus 3 cos theta times sine theta minus cos theta equals 0. Therefore, okay, what have we got? We've got two things. We've got sine theta minus 3 cos theta equals 0 and sine theta minus cos theta equals 0. Correct? And what do? I now, quite straightforward, I'm going to go and solve it. Because what type are they? Okay, they are the sine theta cos theta. So what would I say? I would then say that sine theta is equal to 3 cos theta and sine theta is equal to cos theta. I then divide by cos because I can, because it's sine, cos, and a theta and a theta, a theta and a theta. If those weren't the same behind the trig expression, I'd have to use co-functions, wouldn't I? So here, I then say, therefore, tan theta equals 3 and tan theta is equal to 1. And then basically, I just solve them and I end up with theta equals to 71,57 degrees plus 180k. And over here, theta is equal to 45 degrees plus 180k. All right. So the last gasp, the last thing we can do is when we say, okay, therefore, at the end of the day, we are going to do a substitution for the constant at the end. Pretty heavy, isn't it? Okay. Now, remember, the last thing that you'd be asked in trig is where you've got restrictions. What do I mean restrictions? I didn't say domain, I said restrictions. Remember 1 over x squared minus 9? Straight away we said, whoa, you have got restrictions. Remember my red box on the side? X squared minus 9 cannot be naught. Therefore x squared cannot be equal to 9. Therefore x cannot be plus or minus 3. All right? Now similarly, all right, in trigonometry, what if we had this? Okay, they will ask you, where is this valid? Where is it not valid? Let's say we are asked, 1 over sine x times cos x is equal to something in an equation. This is in an equation. Okay, straight away, look at this. Red flag. We've got something in the denominator. Okay. Therefore, restrictions must apply here. Okay. We cannot have that. So we have our box again. We say, sorry, cannot have that. And we say, therefore, sine x cannot be equal to 0, and cos x cannot be equal to 0, and therefore we say, right, sine x cannot be equal to 0, and cos x cannot be equal to 0. Okay, I'm just going to write them, solve them, and put them in my cannot box. Okay, so I find reference angle equals 0 degrees. Reference angle equals 90 degrees, and sine, and basically I'm going to have here that x equals 0 plus or minus of 360 degree k, and x equals 180 plus 308, 180 plus 360 degrees k, and for the 90 it's a cos, therefore for the 90, this is both for the sine. Let me put them together. Being a bit silly there. Over here, x equals minus, 180 plus 360 degree k. Okay, so in the restrictions are that x cannot be equal to those. And similarly here, x cannot be equal to plus minus 90 plus 360 degree k. Okay. Thus, if x is any of these, if x is any of those, it is undefined. Okay. This is not a difficult section at all, by the way. Okay. The last bit of this, right, is essentially we've got in here, okay, remember we said that x can't be, so whatever we've got under the line, we always look at it and we say, what is here? Okay, and where it is undefined, so where the equation is undefined is where any trig function in the denominator equals 0. So whatever we've got at the bottom there, wherever that is equal to 0, it's undefined. Now, what if we have this? They ask, where is the following function undefined? And they say sine theta, tan theta equals 2. Okay. Where's it undefined? Okay. Well, you'd say, but hold on. That's simple. I'm just going to say that's sine squared over cos, replace sine, factorize, and there, right? Whoa, there's something hidden lurking here. So lurking inside tan theta is this. Remember, tan of theta is sine theta divided by, there it is. Okay, there it is. So inside here, right? Inside there, whenever we've got the tangent, okay? Whenever we see tan, we change to sine over cos theta or x or whatever, and therefore where cos theta equals 0, it's undefined. Okay, and where is that? Okay, I just did it quickly here. Cos theta is undefined, okay, and you solve for that. So we solve for cos theta equal to 0. Reference angle arc cos of 0, okay, etc., etc. I think it's 90 degrees, all right? So we always watch out for tan, but be careful. Here's an example. Where is 1 over tan theta undefined? You'd say, no, be careful. This is 1 over sine theta over cos theta, which is equal to 1 divided by sine theta over cos theta, correct? Which is equal to 1 times cos theta over sine theta. So in this case here, all right, in this case here, it's undefined where sine theta equals 0. All right, so be wary, watch out for those. Okay, the sine theta, cos theta. Where is it undefined? Whatever trig function is below, and where you've got a tangent. So please be careful of that. All right, it is critical that you watch out for it. All right, that brings us to the end of essentially, trig. The last bit is the sine, cosine, area formulas. Those are nowhere near as complicated. We've broken the back of the complicated work. The rest of it now is actually plain sailing to the end. We've got some, the sine, area, cosine rule, which are very easy. We've got some financial maths, and we've got a little bit of probability and stats. Not too heavy going forward now. So, yeah, it's a pretty big moment to have gotten to the end of trig. That last section, very heavy, very tough. Requires you to go through a lot of thought processes and can be very time consuming. Do you know what though? If you get a 7-pointer, hundreds because you followed the recipe, then that's absolutely wonderful. That's what all these videos are about. That's what our time together is about. It's to give you the maximum that you can achieve. That's what it's about. I would say I hope that was fun. It's pretty much a fried brain session, especially this session and the one before it. They're both very heavy. Guys, thanks for watching. I do appreciate you doing so and taking the time to look at these and go through it with me. As I've said before in many other sessions, it is a passion, and it's something that I love doing. It's a subject I enjoy, and I've got a lot back from a lot of my students, and they've all been great. Cheers. Bye.